All right, let's dive into a mathematical breakthrough that cracks problems once considered, well, completely unsolvable. This is the story of how a new way of thinking learned to solve the unsolvable.
So just take a look at this beast of an equation. It's a 15th degree polynomial. Now, the real question isn't just, what's the answer? It's how would you even begin to find a precise, exact root without just approximating or guessing? That's the real challenge we're going to tackle.
For the longest time, an equation this complex was basically a mathematical brick wall. Finding a perfect, exact answer wasn't just hard. For all practical purposes, it was considered impossible.
And look, this wasn't just a feeling people had. It was mathematically proven to be a dead end for a lot of these equations. Abel's theorem is this huge landmark in math, and it basically says that some polynomials simply cannot be solved using traditional algebraic tools. Things like square roots, cube roots, any of that stuff.
So if you can't get a perfect answer, what do? Well, you get close enough. The standard approach for centuries was to use methods that gave you really good estimates of the answer.
And this slide really puts the two different worlds side by side. On one hand, you have the old way, numerical approximations. Yeah, they can get you close, but there's always a risk of tiny rounding errors. But on the other hand, we've got this totally new approach that promises a symbolic, perfectly precise, exact answer.
You see, the problem with just getting close enough is that you're never exactly right. Sure, methods like Newton's method are incredibly powerful, but they work by making successive guesses, which means they always generate these tiny little rounding errors. And in an equation with this much complexity, those tiny errors can pile up, leaving you with an answer that, at the end of the day, isn't guaranteed to be perfect.
But this is where our story takes a really cool turn. What if there was a completely different way to go about it? A new kind of key that could unlock these equations that classical algebra had basically locked shut and thrown away the old key?
And that new key is called Ezouidi's theorem. It's this incredible technique that's designed to find the exact symbolic roots by using a really clever recursive process. It just completely sidesteps the old limitations that had stumped mathematicians for hundreds of years.
Probably the best way to wrap your head around it is to think of it like a mathematical deciphering machine. You feed in the super complex scrambled polynomial on one end, and the machine just works through a set of steps to reveal the simple, clear answer that was hidden inside all along.
Of course, every machine needs an engine, right? And at the heart of this theorem is one powerful recursive formula that does all the heavy lifting.
Okay, here it is. And yeah, I know, it looks pretty intimidating, but trust me on this. We're going to break down what each part of this engine does, and it's actually way more elegant than it looks at first glance.
So, that first piece, the C term, that represents something called binomial coefficients. You can just think of these as like carefully calculated little knobs that the machine turns to adjust each part of the calculation, making sure every piece is scaled perfectly as it unwinds the complexity.
Next up, those L terms, they pull in the numbers, the coefficients, from our original messy polynomial. But the S terms, this is where the real magic happens. This is the recursive part. The formula uses its own previously calculated results to find the next one. It's this beautiful self-referencing loop where each new answer helps find the next.
So how does our deciphering machine actually work? Well, it's a pretty straightforward three-step process. First, we feed it the coefficients from our equation. Second, it runs that recursive formula over and over to calculate a new set of 15 symbolic coefficients. We'll just call them the S values. And finally, these new S values reveal the hidden, simple solution.
Okay, let's turn the key and watch it go. The machine takes its first step, setting a counter, k, to 1. It plugs in the right numbers from our polynomial and churns through the very first calculation.
And bam, look at that. The first thing that comes out of the machine is this. The very first symbolic coefficient, S0, is exactly 0. I mean, this isn't an approximation, it's a perfect, clean 0. So now, the recursion really kicks into gear. The machine takes that first result, that S0 equals 0, and it uses it to help calculate the next coefficient, S1. Then it uses those to find S2, and so on, all the way up through S14.
And this is the truly remarkable part. As the machine just hums along doing its thing, it finds that S1 is 0, and S2 is 0, S3 is 0. It's not just the first one. Every single one of the 15 symbolic coefficients turns out to be exactly 0.
The result is just profound.
As the source material puts it, this isn't just getting close to an answer. The theorem provides a precise, guaranteed to be correct answer for an equation that traditional methods would have just thrown their hands up at and called unsolvable.
So, the huge question is, what does this string of zeros actually tell us? I mean, it's cool, but how does that help us solve that absolute monster of a polynomial we started with?
Well, here's the beautiful part. The theorem uses these S coefficients to basically rewrite the original polynomial in a new form. And since every single one of them is zero, all that mind-boggling complexity, it just melts away.
And after all that complexity vanishes, what are we left with? This: a clean, simple, and perfectly exact answer. The root of that gigantic equation is simply 1.
What the theorem ultimately did was prove that our super complicated polynomial was just a very, very elaborate disguise for a much simpler equation, x minus 1 to the 15th power equals 0. And that immediately shows us the exact root is x equals 1. It even tells us that it's a root with a multiplicity of 15.
You know, this whole thing leaves us with a really fascinating thought. This theorem was a brand new key for a problem that people once thought was permanently locked. It really makes you wonder, doesn't it? What other unsolvable problems are out there just waiting for someone to discover the right key?